What specific challenge regarding speech interaction with LLMs does the Llama Omni model address? And why is this significant in the context of current models like GPT-4o?
The Llama Omni model addresses the challenge of achieving low latency and high-quality speech interaction with large language models, LLMs, which is significant because most existing models, including GPT-4o, primarily support text-based interactions. While GPT-4o has introduced speech interaction capabilities, it still relies on a cascaded system involving automatic speech recognition, (OSR), and text-to-speech, TTS, models, leading to higher latency due to sequential processing. In contrast, Llama Omni enables direct speech-to-speech generation without intermediate text, significantly reducing response latency to as low as 226 milliseconds while maintaining high-quality outputs. This capability is crucial for enhancing user experience in real-time conversational scenarios, where immediate feedback is essential. Furthermore, Llama Omni's architecture allows for simultaneous generation of text and speech responses, which is a notable advancement over the limitations of current models like GPT-4o.
Can you provide a step-by-step breakdown of the Llama Omni model architecture? Please illustrate how the components interact during both training and inference phases.
The Llama Omni model architecture consists of four main components: a speech encoder, a speech adapter, a large language model, LLM, and a speech decoder. During the training phase, the process begins with the speech encoder, Whisper Large v3, extracting meaningful representations from the user's speech instruction, denoted as x_s. These representations are then processed by the trainable speech adapter, which downsamples and maps them into the LLM's embedding space, resulting in the final speech representation, S. The LLM, LLMA3, 1-8b instruct, takes this representation and autoregressively generates the text response, y_t, based on the speech instruction. In the inference phase, the Llama Omni model operates simultaneously to enhance efficiency. As the LLM generates the text response, the speech decoder, which is a non-autoregressive streaming transformer, concurrently processes the output hidden states from the LLM to produce discrete units corresponding to the speech response, y_s. This allows for low latency interaction, as the speech response can begin playback before the entire text response is generated, ensuring a seamless user experience. The entire architecture is designed to optimize both response quality and latency, making it suitable for real-time speech interactions.
Could you walk us through an example that demonstrates how the Llama Omni model processes a user's speech instruction to generate a speech response? Please detail each step and the transformations that occur.
The Llama Omni model processes a user's speech instruction through a series of well-defined steps. First, the user's speech instruction, denoted as x_s, is captured by the speech encoder, specifically the Whisper Large v3 model, which transforms the speech into a meaningful representation sequence, H. Next, this representation is passed to a trainable speech adapter that downsamples the sequence and maps it into the embedding space of the LLM, resulting in the final speech representation, S. The Llama model then takes this representation and autoregressively generates a text response, y_t, based on the speech instruction. Simultaneously, the speech decoder, which operates in a non-autoregressive manner, uses the hidden states from the LLM to generate discrete units corresponding to the speech response, y_s. Finally, these discrete units are synthesized into waveform speech using a vocoder, allowing the user to hear the response almost immediately, achieving low latency and high-quality interaction.
What are the distinct advantages that Llama Omni offers over traditional cascaded systems for speech interaction, particularly in terms of latency and quality?
Llama Omni offers significant advantages over traditional cascaded systems for speech interaction, primarily in terms of latency and quality. Unlike cascaded systems that rely on automatic speech recognition, (OSR), and text-to-speech, TTS, models, which sequentially process speech input and output, Llama Omni enables direct speech-to-speech generation. This architecture allows for extremely low response latency, achieving a latency as low as 226 milliseconds compared to the higher latencies typical of cascaded systems. Additionally, Llama Omni simultaneously generates high-quality text and speech responses, which enhances the overall user experience by providing more coherent and contextually appropriate outputs. The model's design also reduces the required training data and computational resources, making it more efficient while maintaining high performance in both content and style, as evidenced by its superior alignment between speech and text responses.
Explain the experimental validation process of Llama Omni. What datasets were used, and what metrics were implemented to assess its performance?
The experimental validation process of Llama Omni involved evaluating its performance on two primary tasks: speech-to-text instruction following S2TIF and speech-to-speech instruction following S2SIF. The model was trained using the Instructs2S200K dataset, which consists of 200K speech instruction data, generated through a structured process of instruction rewriting, response generation, and speech synthesis. To assess Llama Omni's performance, several metrics were implemented, including content and style scores evaluated by GPT-4o, word error rate (WER), and character error rate (CER) for speech-text alignment, and a mean opinion score (MOS) prediction model called UTMOS to evaluate the naturalness of the generated speech. The results indicated that Llama Omni outperformed previous models in both content and style scores, achieving the lowest OSR-WER and OSR-CER scores, thus demonstrating its effectiveness in generating high-quality speech and text responses.
Discuss any limitations you identified in the Llama Omni approach. Are there specific scenarios where its effectiveness might be compromised?
One limitation of the Llama Omni approach is its reliance on the quality of the speech encoder, specifically the Whisper Large V3 model, which may not perform optimally in noisy environments or with diverse accents, potentially affecting the accuracy of speech recognition. Additionally, while Llama Omni achieves low latency, as low as 226 milliseconds, this performance can be compromised when the chunk size parameter omega is set to a larger value, leading to increased response latency and potentially impacting user experience. Furthermore, the model's effectiveness may be reduced in scenarios requiring highly nuanced or complex responses, as the speech responses are designed to be concise and may lack depth compared to text-based interactions. Lastly, the training data, Instructs2S200K, is constructed from existing text data, which may not fully capture the variability and richness of natural speech, potentially limiting the model's adaptability to real-world conversational dynamics.